Welcome to this lecture series in general topology. In this lecture, we'll discuss the construction of a topology on the product of two spaces. It is a very important construction. Let's recall a little bit. We will not go into any details here. So recall that this map, the addition map from R2 to R, which just adds the two coordinates, is a continuous map. We proved this. And similarly, the multiplication map is also continuous. And of course, we will need the notion of a basis and a subbasis. Recall that a subbasis for R2, meaning a subbasis which generates the same topology as the standard topology on R2, is given by the collection of all the vertical strips and the horizontal strips. We discussed this in the previous lecture. So I'm not going into the definition of a subbasis and that of a basis and everything. I hope you recall them or have them in your notes. Okay. Here are some problems for practice. And now let us get started. So we will define a topology on the product of two given topological spaces. So what is the general philosophy? This is a ubiquitous recurring theme in mathematics. Create new mathematical objects out of old. If we were studying group theory, given two groups, we constructed the product group. In vector spaces, given two vector spaces over a field F, we can construct the direct sum. And this goes on in every field of mathematics. Even if we just had sets A and B, we constructed the Cartesian product. So that's the philosophy. Create new topological spaces out of old. And the most natural notion would be to take two topological spaces, consider their Cartesian product, and somehow give a topology on it, which is useful or meaningful. Of course, you can always put the discrete topology. No, the topology here should interact with the topology on A and on B in some way, in some meaningful way. So that's the kind of thing we want to do. So here's the definition. Suppose X and Y are topological spaces. X and Y are topological spaces. Then we define a topology on the Cartesian product as the coarsest topology on the Cartesian product such that the projections pi x and pi y are continuous. Now, what are these projections? So we have this Cartesian product x cross y. This has two natural maps, one going into x, we call that pi x, the other going into y, we call that pi y. And what are these maps? The first one takes this pair to x. The second one takes this pair to y. So these are natural maps, and if you think of the product as a box, so suppose the horizontal thing has been, or the horizontal side is thought of as x, and the vertical side as y. This is just a tool for thinking. This has nothing to do with the actual shape of the topological space X. Just a way to visualize things. So this pi x map is just like that. You take a point and record only the x part, and the pi y map records only the y part. So that's just a way to visualize these two maps. Okay, so what's going on? See, the Cartesian product is kind of defined by these two maps. These are the characteristic maps for the Cartesian product. And I don't mean to use that as a technical term. I'm just saying it colloquially. This is a defining trait of the Cartesian product that you have these two maps. So naturally, the topology we want to put on the Cartesian product should have something to do with these two maps. And we are demanding that we are endowing the product with the least expensive topology. the coarsest topology which makes these two maps happy, makes these two maps continuous. One could have put the discrete topology here, even then both of them would be continuous. Everything would be continuous in fact. But here we are trying to accommodate only them. As soon as you accommodate both of them, more things automatically come in. The coarsest topology that accommodates for pi x and pi y will also accommodate for other things automatically. We will see that. But as long as these two are happy, that topology is our topology. So the coarsest topology, the intersection of all the topologies which make both of these continuous, is the notion or the definition of the product topology. And whenever we are given two topological spaces x and y, and we write this expression, we write the Cartesian product, unless otherwise mentioned, we will work with the product topology on it. Okay? So that will be a convention. It's a very standard convention. So as of now, the definition might not be clear as to what is the point of this definition. And as we see examples, we will be able to understand this better. For the moment, let us look at a few housekeeping results, very important results, but still somewhat in the abstract realm. We will see concrete examples very soon. So natural question arises, can we locate a suitable or a convenient basis for the product topology? So we have x and y topological spaces, and consider the set B, script B, which is the product of two things, u and v, where u is an open set in x and v is an open set in y. So take the product of any two such things and collect them in a set. That is script B. Pictorially, if we think of the Cartesian product as this rectangle, the horizontal side is x, the vertical side is y. And suppose you take an open set in x and an open set in y. And now what does u cross v look like? So this is pi x inverse of u, and that is pi y inverse of v. It looks horrible. And the common part is u cross v. So all such rectangles are what are fit here, are what are present there in the set script B. And we claim that script B is a basis for the product topology, meaning, well, it is a basis on the Cartesian product, and the topology generated by it is same as the product topology. Okay. So I encourage you to prove it for yourself, but here is the way I'm going to do it. So first we will note that this is indeed a basis. Clearly, the union of all the things here is all of x cross y, because x is open in x and y is open in y. So that condition is fine. We just need to show the intersection condition. So if we pick two elements here, we need to find, so suppose we pick two basis elements or two elements from script B and choose a point in the intersection. We should be able to find another element from script B, which contains this point and is contained in the intersection. So towards that, I'll write probably just one line. So note that this is a basis, since, purely set theoretic remark, you should also try to understand this in terms of pictures, but a formal proof can be given with no difficulty. So we note this, and now this is a basis element, that is a basis element. I meant to write an intersection symbol, I'm sorry. So this is a basis element, that is a basis element, and we have intersected the two. What we get is an open set in X, because intersection of two open sets is open, cross an open set in Y, because intersection of two open sets is open. So the intersection of any two basis elements is again a basis element. So that automatically satisfies the second condition. So this shows us that B is indeed a basis. All right. And now, also, each element of script B is open in X cross Y, open in the product topology. Why? Because U cross V, an arbitrary basis element looks like that, is, again purely set theory, is the intersection of these two things. Set theoretic exercise, please do it. So this is open in X cross Y because what is the topology on X cross Y? It is the coarsest topology which makes pi x and pi y continuous. In particular, it is a topology that makes pi x and pi y continuous. Now, since pi x is continuous and U is open in X, the pre-image of U under pi x is open in X cross Y. Similarly, this is open in X cross Y, and therefore the intersection of them is also open in X cross Y. So we see that the Cartesian product of an open set in X and an open set in Y is open in the product topology. So every basis element or every element of script B is open in the product topology. So now, let's say rho is the topology generated by B. And let tau be the, maybe rho looks bad. Maybe I'll say theta. Theta be the topology generated by B, and let rho be the product topology. I use rho to denote the product topology because rho looks like P for product, be the product topology. So what we have just seen is that theta is contained in rho. Why is that? Every basis element is already open in the product topology, meaning every basis element is already present in rho. So the topology generated by script B will be contained in rho. Because what is this element? What is the definition of this? This is the intersection of all the topologies which contain script B. Rho is one particular such topology, and therefore we have this containment. So we need to do the reverse containment. Okay? But pi x is continuous when X cross Y is equipped with theta. So suppose we equip this Cartesian product with theta, meaning the topology generated by B. We claim that pi x is a continuous function under that. Why? Because you pick an open set in X, call it U. What is its pre-image? It is pi x inverse U. But pi x inverse U is what? This is U cross Y, which is in script B. This is open in X and that is open in Y. So therefore, pi x is continuous with respect to theta, and similarly for pi y. So theta is already a topology that makes both pi x and pi y continuous, and therefore rho is contained in theta. Right? We have a topology that makes pi x and pi y happy. And since rho is the coarsest such topology, least expensive such topology, meaning it is the intersection of all such topologies, it has to be contained in theta. So these two containments now show us that indeed this is a basis for the product topology on X cross Y. We have a convenient basis for this. All right. Corollary, given what we have done, we can prove the following. We have two topological spaces X and Y, and let script S be this collection. In the picture, this looks like all the vertical strips in the picture on the previous page. and then all the horizontal strips. And you should take this as an exercise that this is a subbasis for the product topology on x cross y, meaning first of all it is a subbasis. That is trivial because the union of all of these things is all of x cross y. But the topology generated by this is same as the product topology on x cross y. The reason is very simple. If you intersect two elements from S, you always get something in script B from the previous page, and anything in script B can be obtained by intersecting two suitable elements of script S. So basically using that you can prove this. And here is a very, very important remark, extremely important to know, that the product topology on R2 is same as the standard topology on R2. So what's going on? We can think of R2 as, what did I do? We can think of R2 as the Cartesian product of R and R. Now R is a topological space, and of course R is again a topological space. So we can talk about the product topology on it. I mean, R2 is the Cartesian product of R cross R. There is no thinking about it. Now this is a topological space, that is a topological space. So there is a product topology on R2. But we have already seen the standard topology on R2 by using any distance you like, D1, D2, D infinity. Any three of these, any one of these distances give us a topology on R2 and give the same topology on R2, and that topology is called the standard topology. So naturally we want to ask, are these two topologies different? Both of these topologies are natural in their own way. The standard topology comes from our intuition of geometry. The most natural distance is the D2 distance, the Euclidean distance, so to say. And there you get balls, and balls give you a notion of nearness, and so that's a very natural topology thought of when you think about the geometry of R2, while this is a more formal way of looking at it, a more categorical way if you like. You think of R2 as R cross R, which it is. There is a topology here, there is a topology here, so it already builds a topology for R2. Are those two topologies the same? They are the same. So why is that? Well, we recall that the vertical and the horizontal strips, which are literally now the vertical and the horizontal strips. Here the vertical and the horizontal strips are just for our visual intuition. But in case of R2, they are literally vertical and horizontal. So as we noticed in the previous page, and also, so not the previous page, we noticed in the previous lecture and also during the recall, that the vertical and the horizontal strips in R2 form a subbasis for the standard topology on R2. But what does the previous corollary say? It says that the vertical and the horizontal strips form a subbasis for the product topology on R2 also. So therefore, the product topology and the standard topology are the same. That is one way. But try to prove it more directly rather than going around and around through these corollaries and all that. You know the definition of the product topology, you know the definition of the standard topology. Take that as a challenge, maybe directly, if all of this is unclear. So it's very important to be comfortable with these things. Sometimes thinking of R2 that way, the distance way, or the topology on R2 using the distance way is more convenient. Sometimes this Cartesian way is more convenient. And that depends on the situation. What is the perspective that you need to take? In fact, as we go along, we will see even more ways of constructing the same standard topology on the Euclidean spaces, many different ways of constructing the same thing. R2 is also a vector space. So there is another way to construct a topology on R2 when you think of it as a vector space. Anyway, so I hope this much was clear. And now for the very important thing. So topologies have been constructed. We have some understanding of the topology because we have a basis and a subbasis for it. But really, a topology is there for us to be able to talk about continuity. And this is the heart of the matter. After doing this particular slide, we will look at examples. So suppose we have three topological spaces, X, Y, and Z. And we have a map from Z to the product of x and y. And here this has been endowed with the product topology, since we are not saying anything especially. We will assume that this is endowed with the product topology. And here is a picture. I don't know if this helps, but it's there. Then the following are equivalent. First is that this map is continuous. And the second is that this composite, let me draw this composite map, this composite and the other one are both continuous. So the continuity of F can be broken down to two pieces of information. One is that just look at the x part, forget about the y, project out the y part, just retain the x part, and if this is continuous, and similarly project out the x part, retain the y part, and you find that the other piece is also continuous, then F is automatically continuous. So that is going to be the way we will prove continuity whenever we have a map into a product space. This is 99.9% of the time the way to prove continuity. Suppose we want to prove F is continuous, do not start with an open set here, pull it back and show that this is open here. That will be very, very cumbersome. Break it down into two simpler pieces. And this universal property lets you do that. The proof is trivial. This property is not some difficult thing to prove, but the point is to be able to use it. Okay. So 1 implies 2 is clear. Why is it clear? Well, if F is continuous, we want to show that these two things are continuous. If F is continuous, we already know that this is continuous. The product topology is constructed so as to make them continuous anyway. So this is clearly continuous under the product topology, and therefore the composite is also continuous. Similarly, this guy is continuous. So 1 implies 2 is just the application of the fact that the composite of two continuous functions is continuous. So we will do 2 implies 1. Okay, why is that? So let U and V be open. Yeah, so instead of writing it that way, recall that this thing is a basis for the product topology. Right? So all we need to do, we want to show that, or enough to show that the pre-image of any basis element is open in Z for all U open in X and V open in Y. Right? Since this is a basis, this is a basis for the product topology, we just need to show that the pre-image of every element in the basis is open in Z. Alright, but what is the pre-image? This is, I'll just try to U cross V in a different way, which we have already done in the previous slides. This intersection with that, and pre-images behave well under intersection. Just elementary set theory. Pre-image of A intersection B is pre-image of A intersection pre-image of B. Okay. And what is this? Again, elementary set theory. This is equal to the inverse of this composite, or the inverse image of U under this composite, and the inverse image of V under this composite. Alright, great. But this is a continuous function by assumption. By assumption that 2 is correct, or 2 is true, this is a continuous function. This is open in X, therefore this is open in X cross, this is open in Z. Right? This is a continuous function. U is open in X, so its pre-image is open in Z. So this is open in Z, and similarly this is open in Z, and this is the intersection of two open sets, and hence this is open in Z. That's it. That proves that this guy is open in Z, and this is what we wanted to do. So this proves the universal property, and this is how we will establish the continuity of almost all the maps whenever you have them as mapping into the product. If you have a map from the product to something, then this is not useful. Then you have to think. But if you have a map into the product, this criterion will be almost always useful. Okay, let's move on and look at some examples now. Most important thing. Yeah, so before we look at examples, I need to get out of the way one more thing. So this is just a restatement of the universal property. Suppose we have three topological spaces, x, y, and z, and phi is a map from z to x, a continuous map, and psi is a continuous map from z to y. So just another way to state the universal property is the following. Then there is a unique continuous map, call it F, from Z to the product such that the adjacent diagram commutes. I'll explain, but let me first complete this diagram. So the statement says that there is a unique F continuous. There is a unique continuous map from Z to the product such that this diagram commutes. Commutes meaning what? It means it respects the traffic. So from Z to X, there are at least two different ways. In fact, there are exactly two different ways to go. One is via phi, the other is via F and then pi X. So commutation means this composite is equal to that, and that this composite is equal to that. For this particular diagram, commutation just means that much. So we are saying that whenever we are given two continuous functions, whenever we are given continuous functions, one mapping into x and the other mapping into y, with the same parent, with the same domain, so to say, there is a unique continuous map going into the product of the original targets such that this diagram commutes. And there is no benefit of writing a formal proof once again. It's just a simple application of the previous version of the universal property. How? So first we should ask, let me argue here. So suppose I were asking, how many such f's are there? Forget about continuity for the moment. Here the statement is asking or saying that there is a unique continuous map which satisfies the commutation. Suppose I was asking only for a set theoretic map, just a map which makes this diagram commute. How many such maps are there? Well, there is only one such map. Even set theoretically, disregarding continuity altogether, there is only one such map. In fact, we can explicitly write it down. The map is f of z is equal to phi of x, comma, psi of, f of z is equal to phi of z, comma, psi of z. That's the only map that makes this diagram commute. And it is automatically a continuous map. Because what do we need to show something is continuous? By the previous version of the universal property, we just need to show that its composite with the natural projections is continuous, which it is because we are already given that phi and psi are continuous. So it might sound like a tautology, but it's not. It's a very general way of looking at products in all mathematics. Whenever you have products of two objects in a graph, in a group, in a vector space, in a whatever, smooth manifold, this is the property that defines the product. Anyway, so I hope the statement and everything is clear here, and now we can move to examples. Just give me 1 second. Doesn't matter. So first example is, suppose we are given a map like this, map from R to R square, and this is its definition. You may want to even plot this. So for every real number x, you get a point x square comma x cube. So for 1, you get 1, sorry, I shouldn't do it that way. So what is the value corresponding to 1? It's 1 comma 1. Corresponding to 2, you get 4 comma 8. So it's growing very fast. And yeah, it's maybe something like that. And for negative x's, you will get things like that. So it's some curve in R2. Anyway, we want to show that this function is continuous. And such a nice function anyway we know is going to be continuous. It's just a matter of proving it. There was never any doubt that such a thing is continuous, but we need to prove it formally. Okay, one approach you could take is, again, you can take the epsilon delta kind of approach. We know the standard topology here, the standard topology here. They are kind of defined by balls. So you can, of course, use that. But we will use the universal property, what we just learned. We have R, and then we have, maybe I'll use a different color. So we have R, then we have a map into R2, which we will think of as product of R with R. As we've already established, the product of the standard topology on the real numbers is same as the standard topology on R2, even though the definition of the standard topology on R2 wasn't given like that. We established that those two viewpoints are exactly the same. So anyway, so we have a map from a space into a product space, and we want to show this map is continuous. By the universal property, we just need to show that its composite with the natural projections is continuous. What are the composites with the natural projection? The first projection gives us this map, call it phi. Phi is the map which takes x to x square, right? That's the first coordinate. And psi is the map which takes x to x cube. So this was projection on the second coordinate, this was the projection on the first coordinate, and that is the map psi. This is our map F. Okay, maybe the diagram is a little bit complicated. Let me try to simplify it a little bit. Yeah, maybe this is better. So we wanted to show this is continuous, but by the universal property, it is equivalent to showing that this is continuous and that is continuous. But these we know are continuous just from real analysis, right? You know, these are polynomial functions, and in real analysis, we showed that polynomial functions are continuous. So that's it. That establishes the continuity of this map. And doing this by epsilon delta will be a lot more work. You will have to choose epsilon and then delta carefully, design according to it, and mess around with inequalities. No need to do all that. This is much, much better. Okay, next example. This time we have a map from R2 to R2. It's in some sense the same kind of map. It squares the first coordinate and cubes the second coordinate. We want to show this is continuous. All right. Again, we will use the universal property and basic facts about continuous functions. So we have this map going into R2, which is F. We want to show it is continuous, and again, it is equivalent to showing that the composites with the natural projections are continuous. What is the first composite? Call it phi. Second composite, call it psi. And phi does what? Phi takes x comma y to... It's difficult to accommodate things in this figure. X comma y is going to x square, and here x comma y is going to y cube. Right. So we are left with showing this is continuous and that is continuous. Okay, again, you could do some epsilon delta business, but no, we will exploit our basic facts that we proved about continuous functions. So this we will write as the composite of two continuous functions. Which two functions? Just take, first you project out to the first coordinate, and then you square. So this is the squaring map. This is the projection into the first coordinate. So you start with x comma y, you become x, and then you square that. That's exactly what phi does. And similarly, here you project out to the second coordinate, and then you cube. So all we are saying is that this is continuous, that is continuous. Therefore, this composite is continuous because, of course, the projection maps are continuous. R2 has the product topology. Projection maps are continuous, of course. So this is continuous, therefore, because this is the composite of these two things. And this is continuous by the same reason. And therefore, phi and psi are continuous. And by the universal property, f is continuous. So it's just a matter of diagram chasing. You don't need to write a single thing. Amazing. All right. Another example. This time we have a map going from the R2 to R, and it's defined that way. We want to show it's continuous. And again, such a nice map should be continuous, but we need to prove it. So we have a map from, R2 to R. And here directly there is no way to exploit the universal property. Right? Because the map is not going into a product. This is not a product or anything. This is a product. The universal property is useful when you are mapping into a product. So how do we help this case? Well, first we will do this. First, we have this map going into R2, which we will call capital F, which does what? Capital F of x comma y is squaring the first coordinate, u being the second, just the map that was there in the last example. And now this will be the multiplication map. So maybe I'll draw it here. So this is the multiplication map, which products the two things. So it consumes a comma b and outputs the product of a and b. That map. And this composite is S. Now we know this, whatever. Yeah, this is fine. So this is continuous. We recalled in the beginning. This we proved using epsilon delta, right? The continuity of this we proved using epsilon delta. That's fine. And this we just proved is continuous. So this is a continuous map. So the point I'm trying to convey here is that if you directly use the epsilon delta definition for this particular map, it might be much more complicated than it has to be, because you're messing around with these two exponents. So it's much simpler to prove the continuity of just the most simplest multiplication, which just products the two coordinates, rather than some complicated powers. Okay? So here we are not using the universal property anywhere, but still, this is a nice example. Now, suppose we have a map from R2 to R defined in this way. We want to show it is continuous. Well, so this time we will define this map. We first define this map from going in this direction, call it phi. It will map into R2. And here another map going into R2. No, I just want to keep it R. So what is the definition of phi? Phi of x comma y is this, and psi of x comma y is that. So phi we just showed is continuous. Similarly, we can show psi is continuous. So phi and psi are continuous by the universal property. Therefore, there is a unique continuous map going into R2 such that these diagrams commute, call this map capital F. But what is capital F? Capital F takes x comma y to phi of x comma y comma psi of x comma y. That's the only map that makes the diagram commute, so that has to be capital F, and we know capital F is continuous by the universal property. Alright, so this is a continuous map, and now we will compose with the addition map. This is the addition map which adds the two coordinates. So now this composite is precisely little f. Right? It's just adding these two things. And this we recalled is continuous, we proved it using the epsilon delta method. This we just showed is continuous, and therefore little f is continuous. Here the epsilon delta will be even much more of a nightmare. Okay. Now this is not about the continuity of a map, but showing that certain subset of R2 is closed in R2. So this is a set of points in R2. You can plot it. It's just this particular subset, the graph of the square function. We want to show it is a closed set. And yeah, I mean, if you just go by the definition of closedness, what you need to do is that if you take a point outside this set, there is an open ball that is disjoint with this thing. That's exactly what closedness means, right? I mean, closedness means that okay, let me make a small remark. It's a good thing to maybe do this as an exercise. So let X be a topological space. So this is a small exercise. Let X be a topological space. Let B be a basis for the topology on X. And let A be a subset of X. Then A is closed in X if and only if for all points in X which are not in A, there exists a basis element such that X is in B and B is contained in the complement of A. Looks like a complicated thing, but think about it. So you can use this fact or this exercise to in principle prove the closedness of this, because we already know a basis on R2, it's just these balls. So you can use that, and visually it is clear. You take this graph of, or whatever this set of points is, this is a set of points. Maybe I'll draw it, because why not? It's probably not vertical and horizontal, and that will give me a nightmare. But anyway. So roughly that's what the shape looks like. And whenever you choose a point outside that shape, you can of course visually choose a ball which is disjoint with that shape. And therefore you can write the complement as a union of balls, and hence the complement is an open set. But let's do it in a different and more in a shorter way and somehow a more slick way. And this is the way we will use generally to prove such things. So define the map F from R2 to R as f of x comma y equals x square minus y. Right? Now what are the points where this guy takes the value 0? It takes the value 0 when y is x square. So it's precisely this set. F vanishes precisely at the points of this set. So, and we know that f is continuous. I mean, we did not prove it separately, but by now you should be, by the previous examples that we discussed, you should be easily able to establish that f is continuous. So we know f is continuous. And thus, the pre-image of 0 is closed in R2 in the domain of F. Now why is that? Because this is a closed set in R, or I should say this is a closed set in R, the target of F. The singleton 0 is closed in R, and under continuous functions, the preimage of closed sets is closed sets. You take the preimage of a closed set under a continuous function, you get a closed set. Just like the preimage of an open set is an open set, it follows that the preimage of a closed set is closed set. So this is a closed set, but we just argued that this is precisely that. And that's it. Okay, so we know that this thing is closed. Another example. This is somewhat more abstract. So we have a continuous function from a topological space A to a topological space X. Similarly, we have a continuous function from B to Y. And we are defining this map phi via that recipe. We want to show that phi is also continuous. So we will again just use the universal property. We have a map from the product into a product, and we want to show it is continuous. So to show phi is continuous by the universal property, we just need to establish continuity after composing with the natural projections. So we have these two maps to worry about. Call them something. Let's call this alpha and that one beta. But what does alpha do? It takes a comma b to f of a. And what does beta do? It takes a comma b to g of b. So let's just show alpha is continuous. Similarly, beta will be continuous. And this kind of thing we just did in a previous example. First, you project out to the ath coordinate, or sorry, to the first part there, and then compose with f. So alpha is nothing but the composite of these two things. This is continuous because here we had the product topology and projections are continuous. F is continuous by hypothesis. So alpha is continuous. Similarly, beta is continuous, and that's it. No need to pick an open set here, take the preimage and all that nonsense. No need to do that, even though that will work, but I believe arguing this way is better. Okay. Now for a non-example, we have capital F going from R2 to R, which is defined that way. So when you do not have the origin here, you map that point to this quantity. This is a well-defined quantity only when x comma y is not the origin, because in the denominator we have this thing. This is non-zero precisely when x comma y is not the origin. Okay, so at the points other than origin, you map via this recipe. And at the origin, you just map it to 0, the real number 0. So then we want to make two statements. First is that f is continuous in each coordinate separately. What does that mean? We have the function f. It is continuous in each coordinate separately means the following. Maybe first I will explain geometrically what that means. So we have the coordinate plane. And whenever you restrict f to a horizontal slice, f is continuous. Now what does that mean? Well, a horizontal slice is as good as R, is as good as real numbers. There's a natural way of thinking a horizontal slice as real numbers. So now once you only restrict capital F to a horizontal slice and think of the corresponding function as a function from reals to reals, you get a continuous function. So that is something that I leave as an exercise. Similarly for the vertical slice. So that's what it means to say that f is continuous in each coordinate separately. So f is continuous on each vertical slice, f is continuous on each horizontal slice, where we need to be careful. When we say continuous on a horizontal slice, we mean thinking of the horizontal slice as real numbers. There's an obvious way of thinking this as real numbers. Later, when we talk about subspace topology, we wouldn't need to even mention such identifications. Okay, so this is an exercise, just a matter of writing things down. And f is not continuous at the origin. So even though it is continuous in each coordinate separately, f as a function from R2 to R is not a continuous function. this was continuous at every point when you restrict to a vertical slice or a horizontal slice. So at the origin, f is continuous when you think of it only as a function on the x-axis and only as a function on the y-axis. But as a proper function from R2 to R, f is discontinuous. And to see that, here is a proof. I have in fact written it out in gray. So suppose f was continuous. Let's argue by contradiction. If f was continuous, then its composite with any continuous function will also be continuous. So we consider this guy, this function, call it whatever, call it phi. So it takes x to x comma x. And phi is continuous. You should be able to argue it because we have taken so many examples now. So phi is continuous. What is this composite? This takes x comma y to, this takes x to x square divided by x square plus x square if x is non-zero, and 0 if x is 0. So why is that? Well, if x is non-zero, then this is a non-zero, or this point is not the origin. And then you just use the definition of capital F, you will get that value. Because x is equal to y here, x is equal to y, so this expression becomes that. But at x equals 0, this is the origin, so capital F will output 0. But this is half and this is 0. So this function is taking the value half at all the points except 0, where it takes the value 0. So if you want to draw the graph of this function, it will kind of look like that. Something of that sort. Can't draw an accurate graph. Right, that's the graph, and this is clearly a discontinuous function. So if f were continuous, this would have been a continuous function, but this clearly is discontinuous, and therefore capital F is not a continuous function. So very important to appreciate this difference. Just because you are continuous when you freeze one coordinate doesn't mean you are globally continuous when you think of it as a function on both coordinates. Right? Okay. Now for a little bit more. So suppose we have two maps from a topological space X to R. So F and G are two maps and they are continuous. Then the sum of F and G is continuous and the product of F and G is continuous. So just to recall, what is this function? This takes little x to fx plus gx. So this is what we want to show. Let me argue the first one, the second one will be an exercise. So define capital F as, maybe call it phi. What does phi do? Phi takes little x to fx comma gx. Okay. Phi is a continuous map because when you project out to the first coordinate, you get the function little f. You project out to the second coordinate, you get the function little g. And they are continuous, and therefore by the universal property of the product, phi is a continuous map. And now you just compose with the addition function, which adds the two coordinates. This composite is nothing but f plus g. And that's it. Composite of two continuous functions is continuous, therefore f plus g is continuous. By a similar argument, you can show this second one is also continuous. Okay. Now, if we have any topological space, just a corollary of the previous result, if we have any topological space, then this set, which is the set of all the maps which are continuous, all the maps from X to reals which are continuous, this is a linear subspace of that. This is a vector space. The set of all the maps from any set to any field is a vector space. So this is a real vector space. But by the previous result, by the previous lemma, you can easily establish that this is actually a subspace, a linear subspace. I don't mean a subspace in the sense of general topology. A linear subspace, like in linear algebra. I mean, there is a notion of a subspace in the sense of general topology. We will come to that later, but if you don't know about it, great. If you know about it, just a disclaimer. Here we are talking in the sense of linear algebra. So this collection of all the continuous functions, I meant to write Cx comma R. So this collection is a linear subspace of that thing, just a consequence of this lemma. You can easily prove it. Okay. And I think this should be the last thing that we want to do. I'll leave this as an exercise because we have done enough to be able to do that. Fix a positive integer. Fix a bunch of real numbers under these restrictions. So you take k between 1 and n, and you take l between 1 and n, and you fix those real numbers. So these are n square many such real numbers. And define this function as follows. So you're summing up binomials. These are monomials in two variables, sort of. So these are just polynomial functions in two variables. So all we are saying is that polynomial functions in two variables are continuous. And this is an exercise, but the point is that first you show each of these separately are continuous, and then you're just adding them up. We just showed that sums and products of continuous functions are continuous, and you can just use those things to establish these. Okay, so with that, I want to end this lecture. As usual, like, comment, share, subscribe, and I will see you next time.